All right, so last time we talked about how different substituents would affect the rate, saying that normally speaking, for normal electron demand Diels-Alder reactions, what you want to do is add a donating group to the diene and an accepting group to the dienophile. Probably for the most part, say for 251, when you looked at Diels-Alder reactions, at least one of those two reagents was symmetric. But you can in fact react to asymmetric structures, and if they reacted in this particular way, you'd get a product that looked like this. You could also flip the way that the acceptor approaches the dienophile and instead end up with something that would look like this. Okay, and the way that we describe these two products, it's a little bit incorrect, but we still use it. Normally we would say here for this particular product, the two substituents are ortho to each other, and in the second product they are meta to each other. Now it's not really the best way to describe it because usually the names of ortho, meta, para we use to describe substituents around aromatic rings. There's an aromatic transition state, but not necessarily an aromatic ring in the product, but nevertheless, we still describe them as being ortho or meta. And in terms of which one do you get, it's all dictated by the coefficients and the molecular orbitals that you're interacting. So here we have the highest occupied molecular orbital of the donor, and the lowest unoccupied molecular orbital of the acceptor. And when we bring them together, what you notice is that this is where C1 is and C4. C4 has the largest lobe, and of the acceptor's two carbons, the one down here has the largest lobe. And so we're going to make sure that these come together because overlap equals bonding. So we'll have the largest lobes overlap. And because of that, it dictates that we'll end up with the ortho product. Okay? Turns out that if you used not a one substituted diene, but instead a two substituted diene, right? You could have either the meta product or the para product. And again, we can look at orbital coefficients. From the donor, we would see that here C1 has the largest coefficient, and of the acceptor, right, this carbon still has the largest coefficient. So what we need to do is flip it over, and it would look like this. And then these two would come together in order to start the product formation. And C4 and this carbon here would come together in order to form the product that we want. So that means between these two potential products, we would form the para. Okay? So it's completely a molecular orbital argument as to why it is that you only form ortho or para Diels-Alder products when you have mono-substituted dienes and dienophiles. Now, if this is maybe not something that's so easy to do, right, you got to model what the highest occupied and the lowest unoccupied molecular orbitals look like of your starting materials. You can also rationalize this by resonance or valence bond theory. Okay, and so the idea here is, just maybe bring this up just a little bit. So thinking of this by valence bond or resonance, what we would say is if we had, say, a 1-methoxy diene and acrylonitrile as our dienophile, we could draw a resonance structure for that diene. And that would end up placing a negative charge at the bottom carbon, positive charge on the oxygen. We could draw a resonance structure for acrylonitrile as well. Negative charge would move on to the nitrogen, and we'd have a positive at that first carbon. Then what you'd want to do is line up the pluses and the minuses as they would react together. And then the other two carbons are going to come together as well. This is what dictates in a one substituted diene the ortho product. The same thing is going to be true for a two substituted diene. So if you don't want to do all the modeling, you can do it by valence bond or resonance theory. Okay. The last thing to talk about for Diels-Alder type reactions is endo or exoselectivity, right? The idea that if we had, say, these two reactants and we bring them together, that we could form that ortho product, or we could form that one, depending on whether we have this endo or exo idea. And in this case, this would be the endo product, and this would be the exo. Remembering that when we talk about endo versus exo, if you think about that diene being on the top and the dienophile on the bottom, in this case, we'll have that nitrile group sticking up. If that nitrile group is pointing towards the back of the diene, this is the endo transition state. And that's where your new sigma bonds are going to form. If instead it were pointing away from the back of that diene, this would be the exo transition state. And usually the endo transition state is what's preferred. And the reason why is secondary orbital interactions, secondary orbital overlap. So kind of remembering back to what that means, this is the original description that Woodward and Hoffman gave when they came up with these rules of symmetry. Let's see, where can we go here? Here we go. All right. So the idea that by molecular orbitals and having molecular orbitals be in phase, this describes the formation of the two new sigma bonds. This is your first order interaction. But by placing that substituent pointing back in the endo position, that you would have this favorable secondary orbital overlap, and that's what leads towards the endo product. Okay, the result here is you're going to stabilize that endo approach, that endo transition state, and that's why you end up with the endo product. But it turns out that that's not always true, and it's not always the case. And so the reference that's down here at the bottom, counts chemical receivable, they come up, or research, they come up with a variety of other explanations for why it happens, right? So one of those options could be, or is, that it turns out when you think about the polarity of the molecules themselves, that the endo transition state is more polar. So these arrows here represent the dipole. When it's in an endo position, you're adding those two dipoles together. And when it's in an exo transition state, they're not quite canceling out, but they're at least minimizing each other. And it turns out that when you increase the polarity of the solvent, you increase the amount of endo product that is observed. The other option, thing that you can tell is for steric effects. Okay, so here, the way they're describing this is that X is some type of electron withdrawing group, you know, some type of a carbonyl. So you would have these secondary orbital interactions, and it all depends on what's on the other side. So if this is just a hydrogen, there's not a whole lot of steric interactions when you're using cyclopentadiene as your diene. And so the endo transition state is favored. But once this becomes a methyl group, now there's too much sterics here to support the endo transition state, and instead the exo transition state is more favored. So you can actually drive it towards the exo product just by changing the substituent here on the dienophile from a hydrogen to a methyl group. And a methyl group isn't all that big, but you could make it even larger and see if you could get that ratio to even more favor an exo product. They offer two other explanations for what it might possibly be. One of them, they say it could be hydrogen bonding, not the normal hydrogen bonding that we think of, but just the idea that here you've got some electron density and that has some favorable van der Waals interactions here with this particular cyclopropene dienophile. If you flipped it the other way, the hydrogens would have some steric repulsions with the hydrogen sticking up, such that here you would be favoring the endo. It's not necessarily a secondary orbital overlap, right? Because there's no pi system here to have that favorable orbital, orbital interaction. And so in this particular case, the explanation of the endo product being favored is one of sterics. The other idea is based on electrostatic interactions, that in this particular case, we can use furan, having an oxygen here as our diene, and we use cyclopropene, let's go this way, a cyclic ketone as our dienophile. And here, the electrostatic interactions favor the exo transition state such that you can get the delta negative of the oxygen correlating to the delta positive of the carbonyl, rather than having it flip around the other way and saying that this delta positive has, or this molecular orbital here, has some secondary orbital overlap. It turns out that here the exo is the more favored transition state. So does this totally change how you think about Diels-Alder reactions? Not so much, okay? So you could ask the question, is it the predictions that you use just based on secondary orbital overlap, is it a total coincidence that for the most part they support all of these other ideas, solvent polarity, sterics, hydrogen bonding? Maybe, maybe not, right? For the most part, you can still stick to your secondary orbital interactions when describing the favored transition state for your Diels-Alder reaction. But if it turns out that the exo product is favored as you go through these, you'll need to come up with some other idea. And those ideas can come from, as we just talked about, polarity, hydrogen bonding, dipoles, electrostatic interactions, all sorts of things like that. All right, so that kind of finishes 4+2 reactions. I said you can do a whole host of other types of cycloaddition reactions, one of which would be a 2+2 cycloaddition. Okay, this is a little bit easier to see with models, but models actually don't work well on the document camera, so we're going to have to kind of do it all by visual here. So this would be the frontier molecular orbital method of predicting reactivity, right? That we've got the highest occupied molecular orbital of an ethylene and the lowest unoccupied molecular orbital of a second ethylene. And now we need to start to bring them together. And remember, for the FMO theory, you need to bring them together such that the orbitals are in phase with each other, such that you can get some good bonding. And so they can't really interact in this superficial way, right? Because you would have nice bonding here, orbital overlap, but you would have a phase inversion here. So instead what we need to do is, I tilted one this way, right? So I've got two of the shaded ones sticking up. This particular ethylene, the one that's behind, is adding superfacially on the same face. But now I've had to tilt the one up above such that I get the top of one lobe forming a new sigma bond and the bottom of the other lobe forming a new sigma bond. And so in this particular case, we would say that that reagent is adding anterafacially, meaning on opposite faces. All right, so if you're going to get a 2+2 cycloaddition, it has to be a supra-antera addition. To look like that. Now it turns out if I actually used something like ethylene, or even if I put something else on there, once you do this supra-anterafacial addition, when we put actual substituents on there, we get a whole lot of sterics that otherwise make 2+2 reactions not so likely. The only way, and you end up, instead of getting this concerted reaction, you get a stepwise mechanism. The only way that you actually get a concerted mechanism is if one of those carbons lacks a lot of the steric influence that you see up above by having the carbon be sp hybridized, such that now it's linear. All right, so now we can bring the two together. And in this case, we got to flip the phenyl ring up such that it's out of the way of the pi bond down at the bottom. And we can do this 2+2 addition to get these products. Okay, not just 2+2 kind of in the traditional sense. You can do other types of cycloadditions, right? This is an example of a 1,3 dipolar addition, just to say that this is still a 6-electron transition state, but it occurs where one of the reagents only has 3 atoms as opposed to 4. So here I'm only showing 2 electrons, but that's because I've also got a little bit of movement. I'm going to actually draw it from this one here. We need to add some formal charges. on that particular structure. And so we would say the nitrogen can come down and attack. The double bond is going to break, and we'll add to the carbon up here. Then we need to break a pi bond and donate some electrons back to the original positive charge of the nitrogen. And in that case, we'll end up with the same product that we observed down here. The transition state is concerted, which means that the stereochemistry that you observe otherwise in the starting material is present in the product. Usually 1,3 dipolar additions, the molecules that you're looking at up here are filled with heteroatoms, whether there's 1, 2, or 3. And for the most part, there's not a whole lot of stereochemistry in this particular molecule, although there might be some regioselectivity that you otherwise need to think of. For example, what if I reacted this not with 2 butene, but just 1 propene? You could end up with the methyl group either on the side of the nitrogen or on the side of the carbon. All right. So you might have some regioselectivity issues that you need to think about if you're going to undergo 1,3 dipolar additions. The last kind of cycloaddition reaction that we can talk about would be chelotropics. These are when you have 2 sigma bonds that are made or broken at a single atom. So in the first example here, you have a carbene that's adding to a pi bond. This is a 2 + 2 addition. They can go both in the forward direction as well as in the reverse direction. So down here, right, we have a 4 + 2 where we're going to reform the diene and kick off, in this case, carbon monoxide. Loss of the gaseous product is what drives this particular reaction forward. So here, really it's the same idea. They're just a little trickier to otherwise kind of pull out of a reaction or see within a reaction, because you might not be used to thinking of a singular atom as being the dienophile. All right, but those can definitely happen. All right, kind of the last topic for pericyclic reactions, right, would be the idea of sigmatropics. So it turns out when you take this, let's see, 3,4-dimethyl cyclobutene and you heat it up, you get what you would expect, a conrotatory ring opening reaction. That's the major product that you otherwise observe here, where you end up with cis and trans bonds in the product. You end up with just a wee teeny tiny little bit of the forbidden symmetry, which would occur from a disrotatory ring opening. And you end up with, well, less than 1%, so not a whole lot, of this particular molecule, which is an isomer of the major product. And this comes about from what we call a 1,5 sigmatropic shift. So the product here the starting material has undergone the conrotatory ring opening, but then it's also undergone a second reaction to move a methyl group. All right, and so move a hydrogen, sorry. And then, excuse me, these are what is known as sigmatropic shifts, okay? So, all right, you can tell my voice is going. Let's do this kind of one at a time here, right? So if you look at just the top reaction and you ask, what the heck happened? You would say that you notice that this hydrogen here, it was on the right-hand side, has now moved over to the left-hand side. It is either moved where it was kind of facing forward or facing back. And if we were to draw some arrows that would otherwise explain it, we could say that the sigma bond, the carbon-hydrogen sigma bond, right, that we donated those electrons over, and then we shifted the pi bond over. And this can occur either on either face, so we form a set of enantiomers here. This happens to be a 4-electron concerted system, so this would be Mobius aromaticity, right? We can simplify this as we think about how it would happen just by saying, let's take propene and do the same idea. The idea that we could move this sigma bond over, thus calling it a sigmatropic shift, and then moving the corresponding pi bond. All right, so 4 electrons. If we think about the orbital symmetry and how this would otherwise occur, right, we could do this, the two easy methods that we've talked about. We could do it by frontier molecular orbital. What I want you to do when you think about these starting materials, right, is to maybe take this hydrogen and make it a really long bond, thinking that you've got a cyclopropenyl radical and then a hydrogen radical, okay? And so when we think about it by frontier molecular orbital theory, what we'll do is we'll say there's only 3 electrons in this system. So we're going to look at the second molecular orbital here as our highest occupied. All right, and we're going to choose this one, and then we want to choose the same phase for our hydrogen because we wanted to have a bonding interaction. And what we had said before is when you undergo the reaction, you need to keep in mind that to form the new bond, you need to have orbitals of the same phase. So we need to match the symmetry of the orbitals, which means that this little hydrogen here has to come all the way up to the top on the other side of the molecule. So it's going to react anterofacially. All right, it's got to flip all the way to the other side. The other way that we said we could look at this is by topology, and that means that you take the molecular orbitals of all of your reagents and put them in the ground state. And then recognizing, recognizing that if there's 4 electrons, this is a Mobius transition state, so we need a phase inversion. And so that would mean that this hydrogen couldn't bond down here. It would actually need to go around the other side and bond up at the top of that carbon's lobe. Again, an anterofacial addition. All right. Reality, it's not always that easy to do this, right? Because in terms of bond lengths and bond angles, for 1,3 additions, it's not always considered a concerted process here, with hydrogen being the piece that's moving. But in theory, it's all possible. This is a little bit easier to understand than when we move to a 1,5 sigmatropic shift. So here we can think about this by FMO. Actually, let's do this up top first, right? The idea that we're going to take the sigma bond of that carbon hydrogen and move it over to the other side, and we got to shift the double bonds such that now the hydrogen is attached to the carbon, also bearing 2 deuteriums. By frontier molecular orbital, we're going to choose the 3rd molecular orbital here. And when we move that hydrogen, we need to match the symmetry, so that hydrogen is going to move superfacially from carbon 1 over to carbon 5. And by topology, everything would be in its ground state. We have 6 electrons in our transition state, so we want a Huckel transition state, meaning no phase inversions, so that hydrogen is also going to move from carbon 1 to carbon 5. When we think about the nomenclature here for a 1,5 sigmatropic shift, the 1 refers to the number of atoms that are moving, and the 5 refers to over how many atoms. So we're moving 1 hydrogen over 5 atoms. All right. What else do we want to say about this? That's great for a hydrogen, but what if we wanted to move something bigger? What if we wanted to move a whole alkyl group? All right. Recognizing that if we had, I'm going to do this by topology, a 1,5 alkyl shift. And if we did this by topology, we would say we need 5 orbitals. And we would shade them all in the ground state. And then if I wanted to put on an alkyl group here, it would look something like this. If I undergo the transition, I'm going to move this in a superfacial manner. if I thought about this in terms of a transition state, I'm just going to be moving that alkyl group. I'm not going to change really too much about it. Those three substituents are all going to be kind of in the same place, right? So I haven't done anything really to the stereocenter. And now when I draw my product, I'm just going to have it shifted from one particular carbon to another carbon 5 over. And I haven't done anything really to the stereochemistry, except there. Okay. And so, oops, there we go. All right, so here in total, what we have is a superfacial shift with retention of stereochemistry. Okay. If instead we had a 1,3, there's two ways to consider it, and let's see if this will work for us. We had a 1,3 shift. All right. The idea here is we could also do this by topology, that we've got our group here, and recognizing this is 4 electrons, this is going to go through a Mobius transition state. We need to have some type of a phase inversion. And so at the moment, rather than saying I'm going to pluck this guy up, well, so let's just go this way. So what we could draw for transition state is to say, let's take the small lobe here, and then let's twist it a little bit sideways as our intermediate, or our transition state here. You can see I'm already starting to invert the substituents. And then I'm going to flip it upside down such that I get the phase inversion necessary for a Mobius aromatic transition state here. And so I've shifted this group, a single atom, so it's still a 1,3 shift. I've shifted it on the same face, but I've done it with inversion. So this is a superfacial shift, but with inversion. Okay. If I want to keep it anterofacial, like we talked about before, you'd say, okay, here I did this by FMO, the idea that this is what it would look like, and if I'm going to shift it and pluck it up and turn it over to the other side, I would also be retaining the stereochemistry, but I would be shifting it to the anterofacial side of things. So what that means is a 1,3 shift would either be superfacial with inversion or anterofacial with retention. For some reason now it's zoomed way in on us. Those are what the two of them look like all together. Okay? All right, last set. You can move one atom. The other one you can do is to move 3, or I guess there are others, but really most common would be a 3,3 sigmatropic shift. These you might have heard about before with Cope rearrangements, Claisen rearrangements, and every other version under the sun. All right, in terms of electron movement for a Cope rearrangement, here what we're talking about is we can move the double bonds over, breaking a sigma bond and forming a new sigma bond here. It's a cyclic transition state, 6 electrons, Huckel aromaticity. Whether you draw those arrows kind of moving towards a counterclockwise fashion or a clockwise fashion, it doesn't really matter. You can make it go a little bit faster by putting an oxygen group on there. What's nice about it too is that after you go through that Cope rearrangement, you end up with this enol that undergoes a tautomerization to, in this particular case, an aldehyde. It could be a ketone otherwise. Claisen rearrangement looks exactly like a Cope, except there's an oxygen embedded within that 1,5 diene. As you go through the rearrangement, then you end up forming, and here I can draw my arrows in the opposite direction, you end up forming an aldehyde. In this particular case, an iron-link Claisen happens to be when you start with an ester. You need to form another alkene, because right now there's only one alkene and a sigmatropic shift here would require 2. So LDA is your strong base. You can deprotonate here and then trap that enol with TMS chloride, tetramethylsilyl chloride, just abbreviated TMS. Now it'll undergo something that looks like a Clancy rearrangement to show here. Under the aqueous workup, this TMS falls off, and you've basically undergone the 3,3 sigmatropic shift, converting that ester into a carboxylic acid as well. Sorry. In terms of how do you draw this, or how do you think about this, sigmatropic shifts are really quite nice because they undergo a chair transition state. All right, and the idea here would be, I'm just going to flip this one over, that if you had, let's do a cope rearrangement here. Maybe I started with this enantiomer as my starting material. The question is, what happens then to that stereochemistry as I go through the transformation? So I can draw the arrows. And somehow I end up with a di-substituted diene here. And the question is that methyl group oriented such that it is cis or trans? Okay, and we can do this all by mapping this onto a transition state. All right, so I'm going to use a light color just to kind of draw myself a chair so that I have an idea of what I'm doing. All right. Then I'm going to map my starting material onto this. Okay, so I would say I've got my double bond, moving over here. The methyl group is sticking up, so I have to put it in an axial position. And then I've got just a plain methylene, and then another CH2. So if I look at this chair transition state, I can ask myself, is this the most stable conformation? And you would say no. So we need to do the ring flip, or to a more stable conformation. And in that case, that is what my starting material looks like. Here are my 2 substituents. The methyl group is still up. Then I can say, good, this is the more stable chair transition state. Now I can go ahead and react it, form my new sigma bond, form my 2 new pi bonds. Don't change anything about the molecule, meaning leave it in that chair conformation. But go ahead and follow everything that you did with the arrows, right? So I made a new sigma bond. This pi bond is now just a regular sigma bond. The one down here is a pi bond. I gotta leave my substituents just as they were. I broke this sigma bond. I got a new pi bond. That's just a sigma bond. Okay, so now if you look at this product, notice that I'm gonna put in this other hydrogen here, that the methyl group and the other substituent to it are trans. All right? And so the cyclic transition state will predict the structure of the product. All right, so that kind of finishes all the pericyclic reactions. All right, this is just kind of a general overview in terms of selection rules. We said that electrocyclic reactions, if you're in this Mobius transition state, you're going to undergo conrotatory ring closure. If you're in a Huckel transition state, it'll be disrotatory. For the 4n+2 system for cycloadditions, these Diels-Alder reactions, it's going to be superfacially coming together. If it's a 2+2, for example, it would be supra plus antera. The same selection rules would follow with other types of transition states, right? If you had a 4+4 cycloaddition reaction, that would be a Mobius transition state, and it would be supra-antera facial. If you've got a 4n+2 sigmatropic shift, like a 1,5, this would be superfacial with retention. And if you had a 1-3, you could think of it as either antera with a retention or superficial with inversion. All right. But again, just kind of going back to the idea that the molecular orbitals tell you how the molecules are going to react together. Remembering that if you're going to make a bond, you need to either think about it by frontier molecular orbital theory, where you need to match symmetry and match orbitals that have large coefficients in order to form bonds. If you think about it by topology, or let's just say topology, the idea that if you're going to go through a Huckel transition state, there are no nodes, and if you're going through a Mobius transition state, there should be one node. All right, but really with a concerted transition state, the stereochemistry is predicted by molecular orbital theory. All right, that's going to be it.